right, looks like most of you are back in. All right, so we're going to pick up where we left off yesterday. We derived these formulas for the rates of change of energy and angular momentum across a surface at infinity, so how much energy and angular momentum is leaving the system. And we derived almost identical formulas for the amount of energy and angular momentum falling into the big black hole through the event horizon. Okay, now we need to say, what is the stress energy tensor T in the case of a gravitational wave? So we're going to motivate it just by looking at the linearized Einstein equation. Rather, let me correct that. This is the full vacuum Einstein equation, the linear piece, the quadratic piece, and then omitting cubic pieces. So this thing here, the quadratic piece, is acting as a source for changes in the system, H. So that means we can think of this as a kind of stress energy tensor. So this is an effective stress energy. It is creating gravitational perturbations. So you have gravitational waves, they're oscillating, they'll beat together against each other in here, and that will create effective stress energy. Let's make this a bit more precise by referring back to the two-timescale expansion. So remember that we're looking for rates of change of the orbital parameters and the mass and angular momentum of the big black hole. And remember we had that H1 was a function of our, or let me had it before, XA, T tilde, and the T tilde dependence came into dependence on a few things, one of which was, say, the mass, the correction to the mass of the big black hole. Looks schematically like this, delta m over r, and this is evolving as a function of slow time. And we'll also have a correction to the big black hole's spin. It's going to look like this, delta J over r squared, and delta J is slowly evolving with time. Now let's think, okay, we've got a big black hole here, we've got a particle going around here. Then the mass and angular momentum that you measure in the system is going to depend whether you're evaluating it in a region inside the orbit, or if you're evaluating it in a region outside the orbit. If you're outside the orbit, if you're looking at the total mass or total angular momentum, you're going to be including the mass and angular momentum of the particle. Whereas if you're looking in here, you're only going to see the mass and angular momentum of the big black hole. So let's say in this region, say this is at a radius r0, time-dependent radius, so this is moving around, maybe it's an eccentric orbit. But a radii smaller than that radius, you're going to be able to measure corrections to the big black hole's mass and corrections to the big black hole's spin. And once you go out here, you're going to add additional things, which are coming from the particle. So this is very schematic. The dependence on r is basically just the leading dependence as you go to large distances. But schematically, it looks like this. So then you have the energy of the particle looking like a mass term. That's slowly evolving with time. And then you have the angular momentum of the particle, which is also evolving slowly with time. So what we're looking for is the rates of change of these quantities due to the fluxes of energy and angular momentum out to infinity and down into the black hole. So how do we get that from this effective stress-energy tensor? So remember, in the two-timescale expansion, we had an equation a second-order equation move this to the right-hand side so it looks how it looked before. So we've got this quadratic term constructed from products of first-order mode amplitudes. And then we had this term which was coming from slow time derivatives of the first-order metric perturbation. And also corrections to the frequency. Okay, but in here, I'm only looking at the things that are purely slowly evolving and have no oscillatory behavior. I'm not looking at the mode amplitudes of wavy solutions. Here I'm only looking at the pieces that are slowly evolving. So remember yesterday I said you can really only think of averaged effects of gravitational waves leaving the system. And so these are the averaged things. These are things that average out the fast waves. And it's in these quasi-stationary pieces where you can actually identify, okay, what do I mean by the correction to the mass? What do I mean by the correction to the angular momentum? In the oscillatory modes, we don't have well-defined mass and angular momentum contributions. It's only in the slowly evolving pieces that we have those quantities. So let's look at just the zero frequency piece of this equation. That means setting k to be 0. But the important thing to realize is that the zero frequency piece of this quadratic operator is coming from pieces of the first order metric that are not quasi-stationary. They're coming from oscillatory things. So that's because you can have modes beating against each other. So you get e to the I plus k alpha psi alpha, and then e to the minus I k alpha psi alpha. So you can have two modes with opposite phases that then cancel and just give you one, or rather give you the product of the amplitudes, whatever amplitudes are next to them. And that's where the gravitational waves come in. So this is the form of the gravitational wave, and then you have gravitational waves beating against each other to create a stationary term here. And now, in this term, we're just looking at the zero frequency pieces of the linearized Einstein tensor constructed from the zero frequency pieces of the first order metric perturbation. And And so the zero frequency pieces of the metric perturbation look like that. At least the gauge-independent pieces look like that. So this, remember, the 1 here means you're including one slow time derivative in the operator. So this thing here is going to look like delta m dot over r plus delta j dot over r squared, with maybe some other radial dependence coming from the radial dependence of this, plus E naught dot plus LZ dot. So it's in here where the rates of change of the mass and angular momentum come into play in the Einstein equation. And for the zero frequency part, it turns out you can ignore this entirely. So this only contributes gauge effects, but this part includes gauge invariant effects. So what you get is that the slow variations of the system are just driven by the zero frequency part of what I was calling the effective stress energy tensor of the gravitational waves. So I'm being very schematic here. You have to actually go through a detailed calculation to see why this works. But this is the basic idea. So getting a bit more specific, a bit more precise, we're going to say that 1 over 8 pi times delta squared g alpha beta 0, 0, that this quantity is the effective stress energy tensor of the gravitational waves, almost. Actually, no, in totality, this is the full thing. What's another way to write this? We can write this just as an average over the phases, because we're just picking off the zero frequency bit, which corresponds to averaging out the fast oscillations. So it's 1 over 8 pi times the average, delta squared g 0 alpha beta, where this 0 just means I'm ignoring slow time derivatives that appear in this operator, and I ignore omega 1 corrections to the frequencies. And the average here means an average over the phases. You integrate from 0 to 2 pi over the radial phase, and you integrate from 0 to 2 pi over the azimuthal phase. Actually, I can drop this. So this big quantity here is the effective stress energy tensor of the gravitational waves. And so now you can just evaluate this at infinity to get the fluxes of energy and angular momentum at infinity, or you can evaluate it at the horizon to get the fluxes of energy and angular momentum at the horizon. And that's enough information to do the adiabatic in Sparrow. We just needed these fluxes. So you go through the procedure I outlined yesterday, start with an E0 and an LZ. That selects a geodesic. You calculate the waves that are sourced by that geodesic. You then calculate the fluxes using this stress energy. That gives you an E dot and L dot. And you then update to the next geodesic. Okay, any questions about this before I move on to the next topic? Okay, the next topic is going to be totally different. So this was just the most naive calculation you can do. This is something you can do just by assuming that the balance laws hold true and you don't know anything about the self-force. Now I'm actually going to go into deriving what the self-force is and how you can do more complete calculations. So this calculation only works for orbits in Schwarzschild or for equatorial orbits in Kerr. But you need to know the full self-force in order to do any better than that. So in order to do even adiabatic inspirals of generic orbits in Kerr, because you need to know how the Carter constant is evolving. And certainly to go to post-adiabatic order, you need to know much more about the self-force. Okay, so how are we going to derive what the self-force is? We're going to use a method called matched asymptotic expansions. So far, we've been assuming that at linear order, we can treat the small object as a point particle. Now we're going to forget about that picture and move away from that picture. And here's why. So if H1 is sourced by a point particle, or a point mass, so you've got your little point mass of mass little m. You look at how the field depends on the distance r away from the particle. Well, then very near the particle, H1 is going to look like just a Newtonian potential, m over r. So that diverges at the position of the particle, as you'd expect for a point mass field. But now, what does this say about the Einstein equations? So let's remember the equations we'd written down. So here we have linearized Einstein equation for H1, sourced by a point particle stress energy tensor. And then second order, so here we're stepping back from the two-timescale expansion. We're considering something much more general. We're just thinking of this point mass in an arbitrary vacuum space-time. It doesn't have to be Kerr, it can just be any vacuum background. Okay, so one thing is it's not clear what this correction to the stress energy tensor should be, but let's just ignore this entirely for a second. Now let's look at the second term that appears in the source, which is the second order Einstein tensor constructed from H1, so constructed from quadratic terms in H1. Remember, the structure of this quantity was like a derivative of H1 times a derivative of H1 plus H1 times two derivatives of H1. That was the general structure. Now, if we put in H1 is m over r near the particle, well, a derivative of m over r is like 1 over r squared. Two derivatives of m over r is like 1 over r cubed. So here we have 1 over r squared multiplied by 1 over r squared. Put that m back in. So that's m squared from the two factors of h over r to the 4. In this term you have 1 over r times 1 over r cubed, so you still get 1 over r to the 4. Now this divergence is so strong that this quantity is not well defined as a distribution in a region that includes r equals 0. So what does that mean? It means that if you integrate this quantity against a test function, a smooth test function, well defined as a distribution, if you integrate it against a test function, you do not get a finite result. So here's integral against just a smooth test function phi, or in general you'd have to make it a test tensor phi, integrated over some space-time volume, so this is a 4-dimensional volume element. And let's just integrate over a patch around the particle. So we can just choose our test function to vanish outside a small region, say of radius capital R. So this integral gets cut off at a radius of capital R. So we put in 1 over r to the 4 for the delta squared g. And let me just drop indices in both quantities. And now the volume element, as you get really close to the particle, you're looking at a very small patch of space-time, so it looks just like flat space. So here you've got r squared over r to the 4. So you have 1 over r squared. And you integrate this over r. And you get m squared over r, evaluated between 0 and capital R. And you see, this is infinity. So what this means is, basically anytime you're solving a partial differential equation, what you're doing is performing an integral over the source that terms in the right-hand source that appears on the right-hand side of the partial differential equation. And you'll have maybe some Green's function multiplying that source. What this is telling you is that that integral over the source always blows up. No matter what point you're trying to obtain a solution to the PDE, you always get infinity as your result. So this is a manifestation of a general statement in GR, proved by Garrosh and Trashin in the 80s. That statement is the exact, so fully nonlinear Einstein field equation with a point particle source, or a point mass source, has no solution within a space of functions that are well-behaved in a suitable way. So within a space of well-behaved functions. Where well-behaved here means that the Einstein tensor, constructed from some metric, so here I'm not talking about a background metric, I'm talking about a full metric. Well-behaved means that this is well-defined as a distribution. So this is a very general result, and this is just an example of why point particles are not well-defined in a straightforward sense. Now, that doesn't mean you can't work with point particles. You can work with point particles, as Luke does in post-Newtonian theory. But if you do, you have to adopt some regularization scheme and some renormalization scheme. If you're just going ahead, plowing in, just trying to use ordinary PD theory, it doesn't work. Okay, but why physically does this happen in the Einstein equations? Well, physically it happens because if you're trying to shrink a finite mass object down to the size of a point, you never get a point particle, you get a black hole. So once you've compressed the matter, or compressed the mass into a sufficiently small volume, you always get a black hole, you don't get a point particle. But now, specifically, what is going wrong with our treatment here? What's going wrong is that near the small object with mass m, m itself dominates the gravity, or the space-time. So imagine we've got a big black hole, mass m, somewhere out here. We've got our little object, black hole or neutron star or whatever, with mass little m. In most of the space-time, this creates a small perturbation on top of the background of this big black hole. But if you're looking in small regions near the small object, well then no, the small object is dominating the gravity. It's not the big object dominating the gravity. So we've assumed that we can write that the exact metric is the background metric plus corrections coming from the small mass. But this expansion does not make sense in this region here. It's not accurate, so it's not surprising that things are going wrong. So this is where the method of matched asymptotic expansions comes in. And the idea is, you've got this big space-time, this thing's going around. In most of the space-time, you use this expansion, but then you zoom in on this region around the small black hole. So on a scale of distance r of order the small mass, in this region, we introduce a different expansion of the same metric, but now it's expanding around the metric of the small object itself as if it were isolated. So if it's a small non-spinning black hole, for example, this will just be the Schwarzschild metric with mass little m. But in this expansion, everything's going to be a function of r over m, or of m over r. So this is the natural length scale that comes in. And so, for example, if this is Schwarzschild, we know we're going to have terms like this, where the dependence on r always comes in the form of m over r, or r over m. And now we have corrections that are coming from the interaction with the external spacetime. So this is kind of the schematic structure, but now let's make it a bit more concrete. Let's adopt Cartesian coordinates, or pseudo-Cartesian, or quasi-Cartesian coordinates, T, X, A, that are centered in some suitable way on the small object, so on little m. Then define scaled coordinates, scaled spatial coordinates, x bar a is xa over epsilon. So remember, we can think of epsilon as basically just being little m. So all I'm saying here is that this is an expansion in powers of epsilon at fixed values of this coordinate, not at fixed values of the original coordinate. So the outer expansion, which is what I'll call this whole thing, will be called the outer expansion. This is performed by performing an expansion as epsilon goes to 0 at fixed coordinate values t, xa, the unscaled coordinates. Or it could be performed in different unscaled coordinates that are not centered on a small object, but centered on the big object or anything else. But the point is that they're measuring things essentially in units of the external length scale, which for us is capital M. Now this I'll call the inner expansion. And that's performed by taking epsilon to 0 and doing an expansion in that limit at fixed values of t and x bar a. So you perform a coordinate transformation to the scaled coordinates, and now you do your expansion in powers of epsilon. So what do these two limits correspond to physically? On the outer expansion, you're looking at the limit where the small mass, the small object, is shrinking down to 0 mass and 0 size, while holding external length scales, such as capital M, while holding those fixed. So the object is shrinking down to 0 size, everything else is staying the same. And then in the inner expansion, instead, you're holding the size of the small object fixed and letting all the other distances grow to infinity. So you're still looking at the same ratio, that the scale of the small object is small compared to other scales, but rather than the small object getting smaller and smaller, other scales are getting bigger and bigger. So let's plot a couple diagrams where we can look at the limit. So here, I'm just defining r from the coordinates, from the Cartesian coordinates, in the usual way, x squared plus y squared plus z squared, square root. And now how do the two different limits look on this phase diagram? Well, the outer expansion is just taking epsilon goes down to 0 at fixed values of r. So this is the limit in which the outer expansion is taken, whereas the inner expansion is at fixed values of this divided by epsilon. So those curves are straight lines that converge down to the origin here. So this is the limit in which the inner expansion is taken. So essentially, these lines are following the small object down towards 0 size. Or we can plot these curves in epsilon and r bar coordinates. So in this case, the lines going straight down are now the inner expansion. Epsilon goes to 0 at fixed r, or at fixed r bar. And the outer expansion is now going out. We're following lines that go out to infinity. Okay. Now we've got two different expansions, and where the matching part of matched asymptotic expansions comes in is that we say these are two different expansions of the same metric, so they have to agree with each other in a certain sense. Now, there's actually a variety of different ways of formulating a matching condition. I'm actually going to take basically the weakest condition, not quite the weakest condition, one of the weakest conditions that we can assume. So the two expansions need to match. Now, to see what I mean by the matching, I'm going to first write the two expansions in a slightly different form. Where rather than introducing lowercase h's and uppercase h's and g object superscript, I'm just going to use the same symbol I use for the exact metric, but just introduce superscript n, indicating the power of epsilon. So this is also a function of time and angles, but all we care about for the schematic picture here is its dependence on r. So this is the outer expansion. We have powers of epsilon and functions of r. Then the inner expansion I'm going to put a bar on top of the g rather than a tilde. Each of these coefficients are functions of r bar. This is the inner expansion. Now let's take these two expansions and re-expand them so that they're functions of the same variables, and so that they're both in the form of double expansions for small values of epsilon and small values of r. So small values of r mean that you're near the small object. So let's expand the outer expansion, or re-expand the outer expansion, near the small object, meaning r is small. So much smaller than capital M, for example, but just Let's call it epsilon to the 0. Then we have the exact metric as a double expansion. We've now re-expanded each of these coefficients when r is small. So we've got epsilon to the n, and then a power series in epsilon to the p. No, let me write that as r to the p. G tilde n p. So the p label labels the power of r. And right now I'm not restricting whether p can be positive or negative. It's just a general power series. And now these coefficients do not depend on r, they just depend on time and angles. So let me erase this middle sum and just put a p down here. So we've got this as our summand. Okay, then let's re-expand the inner expansion. Far from the object, meaning that our bar is much, much bigger than 1, or meaning that r is much, much bigger than epsilon. Let's re-expand the inner expansion far away from the object. So then we've got g tilde alpha beta is sum over powers of epsilon to the n, and now we've got epsilon to the p over r to the p times these coefficients, g bar n p alpha beta. So here I've got functions of r bar, and I'm taking r bar to be large. So now my small quantity here is 1 over r bar to the p, which is just epsilon to the p over r to the p. So in this case, we now have epsilon to the n plus p, r to the minus p, g bar n p alpha beta. Now the matching condition is that these two expansions have to agree with each other, order by order in epsilon and r. So if you have epsilon times r squared in this expansion, then the coefficient here has to be exactly the same coefficient as when you have epsilon times r squared here. So all we've done is taken the exact metric, expanded it in one way, expanded it in the other way, or expanded it in the second way and then in the first way. So we've just done two expansions in two different orders. Yeah. Right. So G bar 0 here is G object. G tilde 0 is just G. What's that? Yes, bar down here, tilde up there. Yeah. Okay, so these need to agree term by term. And that's basically just a statement that the functions are sufficiently well defined that if you perform the two expansions in two different orders, you get the same result. So when we equate coefficients of powers of epsilon and r between this expansion and this expansion, we get the condition that g tilde of np alpha beta has to equal g bar of n plus p minus p alpha beta. So the minus p just comes from the fact that this is r to the minus p, whereas this is r to the plus p. And then the n plus p comes from the fact that this is epsilon to the n plus p, and this is just epsilon to the n. So this is the matching condition. These coefficients have to be identical to each other. Now, thinking more physically, what do these two expansions mean? What they mean is you're looking at a region where r is small, much, much less than, say, capital M or epsilon to the 0. We stick with epsilon to the 0. But it's much bigger than epsilon. As in this region, I think it's called the buffer region, where you would actually expect this double expansion and this double expansion to be an accurate solution. So these are distances that are large compared to the size of the small object. So say out here somewhere. Actually, you should make this object way, way smaller to make this a little bit more accurate. So we've got a very, very small object, little m. We have this little region around it with distances of order little m. Then we have a region that's large compared to the size of little m, so r is much bigger than epsilon, but it's still small compared to the external length scale. So let me make this also dramatically bigger. It's still not quite accurate because this does not look small compared to that, but just imagine that this orange region is small compared to the size of the big mass or compared to the size of the orbital radius, but it's still big compared to the size of the small object. So that's where you'd expect these two expansions to be accurate. So you expect the inner expansion to be accurate when r is much, much smaller than epsilon to the 0. You expect the outer expansion to be accurate when epsilon is much, much smaller than r. And you expect this double expansion to be accurate when you're satisfying both of those conditions simultaneously. Okay, now this matching condition becomes a little bit clearer, I think, if you draw the terms in a table. So to do that, let's first find out some restrictions on the expansions coming from this matching condition. So a consequence of the matching condition is that since g bar n plus p minus p alpha beta equals 0 for all values of n plus p less than 0, then we must have the g bar n p equals 0, sorry, g tilde n p equals 0 for all p less than minus n. So because you can't have negative powers of epsilon in your outer expansion, sorry, in your inner expansion, That puts a restriction on the allowed powers of R you can have in your outer expansion. So G tilde 0 alpha beta is the zeroth order term in the outer expansion, and that's just the background spacetime. So let me state this more clearly. G tilde n alpha beta starts at order 1 over r to the n. So you can't have 1 over r to the n plus 1 or 1 over r to the n plus 2 or anything like that. The most you can get is 1 over r to the n. And by the same kind of reasoning, no, stick with that. So that means it starts at order r to the 0 for the n equals 0 term. 0 alpha beta, and then you get higher powers of r. So the smallest power of r for the n equals 0 is r to the 0, and then you get all higher powers of r in your expansion for small r. And I'm just defining the coefficients to be g superscript p. Then your first order perturbation in the outer expansion, which is g1 alpha beta, and we're calling that h1 alpha beta. That's n equals 1, so it starts at order 1 over r. So we have 1 over r, and I'm going to write the coefficient as h alpha beta 1 minus 1. So the 1 here is the power of epsilon, the minus 1 is the power of r. And then you have higher powers of r. And similarly, g tilde 2 is h2 alpha beta. And this is telling us that the most singular power in r is 1 over r squared, because n equals 2. So we have 1 over r squared, h2 minus 2 alpha beta, plus 1 over r, h2 minus 1 alpha beta, plus r to the 0, h2, 0, and so forth. And then you go down to an arbitrary term. We have g tilde n alpha beta equal to h n alpha beta. And we start at order 1 over r to the n. And then we have higher order terms in r. And now, here I'm writing each row in my table as the expansion of a piece of the outer expansion for small values of r. Now, the matching condition is telling us how that relates to the terms in the inner expansion. What happens is that each column here corresponds to a term in the inner expansion. So the sum of all these terms here correspond to the small objects metric expanded for large r, or large r bar, sorry. Then this next column is H1, capital H1, where the sum of all these is capital H1. Next column is capital H2, and so forth. So each row is a term in the outer expansion, each column is a term in the inner expansion. And the coefficients, like this, always have to agree term by term. You always have the same coefficients. So the main thing to get out of that is the fact that that first column, which is the highest power of 1 over r in the outer metric perturbations, every term in that corresponds to a term in the small objects metric. So h, n, minus n, alpha beta is g bar 0, n, alpha beta, which is g object, and I'll give it again a superscript n, alpha beta, where each of these terms is an expansion at large r bar of the object's metric. So this is 1 over r bar to the n. And the coefficients here are these coefficients. So as you zoom in towards the object, the leading term in your nth order outer metric perturbation is just identical to a term in the large r bar expansion of the object's metric. So remember, large r bar means you're zooming out to asymptotic infinity in the metric of the small object, going far away from the small object. Now, one thing you may not know is that if you have an asymptotically flat spacetime, or at least a quasi-stationary asymptotically flat spacetime, and if you expand it near infinity, then you can define multiple moments of the spacetime just from the form of the metric at infinity. So to think of why that makes sense, think of Newtonian gravity or electrostatics, and say you have some matter distribution and you're going far away and it's producing some potential. Then you can perform a multipole expansion of the potential. You get the total mass of this matter distribution over R plus mi ni over R squared, where ni is a unit vector pointing radially outward, and this is the mass dipole moment, or if you're looking at electrostatics, it would be the electric dipole moment. That's telling you how far away from the origin, so say this is the origin, it's telling you how far away from there the center of mass of the blob of matter is. So it's the displacement of the center of mass away from the origin. So you can always just choose a coordinate system in which the origin is on the center of mass, and then this term will vanish. And then we have the quadrupole moment, and so forth. So in Newtonian gravity, or in electrostatics, you would be used to identifying the moments as integrals over the distribution of matter or of charge. But you don't need to define them like that. You can define them just by going to large distance and defining them as the coefficients that appear in this expansion. And that's how things are done typically in GR. You define multiple moments of the space-time by looking at the large R expansion and reading off coefficients in a particular way. So one consequence of that is that it allows you to define multiple moments for black hole spacetimes. So if you were defining multiple moments as integrals over some matter distribution, that would not make sense for a black hole where you don't have any matter. It's just vacuum. But this kind of definition, where you're just reading off coefficients of powers of 1 over r, that is perfectly well defined for black hole spacetime. And so that means that the expansion we're doing here works equally well for black holes as it does for small neutron stars. So G object n, the coefficient of 1 over r to the n, is determined, or you can say determines, is determined by the nth, is it nth or nth plus 1? And minus 1. Yeah. N minus 1th multipole moment of the space-time. So just like we have in the Newtonian case or in electrostatics, the 1 over r term is going to define for us what we mean by the mass of the space-time. And since this is the space-time of the object as if it were isolated from everything else, so isolated from the rest of the universe, we can then just say, we can just identify that mass as the mass of the object itself. Then order 1 over r squared, we're going to have a mass and dipole moment telling us whether the center mass of our object is displaced slightly from the origin of our coordinates. And remember, the origin of our coordinates are some Cartesian coordinates that we're saying are centered on the small object in some effective way. So that means we want to just choose the mass dipole moment to be 0, because we want our center of mass to be on the center of that local coordinate system. Then at next order, 1 over r cubed, you have mass quadrupole moment. But one thing that's different about GR than about electrostatics or Newtonian gravity is you actually double the moments. So you don't just have a mass dipole moment and a mass quadrupole moment. You also have spin dipole moment, which is just spin, and you have spin quadrupole moment, and so forth. So the only one where you don't double it is just the mass. So you're not matching, you won't ensure that if you try to match at a single radius, at a single value of r. But you will ensure that if you're just treating these as functions and matching all the powers of r. So you're looking at a range of r values and making sure that you match in that entire range. And yeah, then the derivatives will automatically match just because you're taking derivatives of the same function. Yeah, exactly, yeah. So rather than multiple moments, I should say multiple moments. We have mass moments that have n minus 1 indices for the n minus 1th moment. So these are the mass multiple moments. And then you also have spin multiple moments or sometimes called current multipole moments. Okay, so now let's start writing down H1 and H2. Because remember, we're really only interested in going to second order, even though here I'm describing something that works to any order. So now H1 is going to be m over r plus order r to the 0 and higher order in r. So this is the dominant behavior as we get to small values of r. And this mass is the mass we define from the multipole moments of the object's metric. So it's actually, if you've learned about ADM mass, it's the ADM mass of the metric G object. Then at second order, well, we're going to have things like m squared over r squared, but they're still determined just by the mass. But then we get the dipole moments, mi, ni, and the spin moments always come with a Levi-Civita symbol. So the new information that appears at second order is the mass dipole moment and the spin of the small object. And we're going to set that to be 0, make our object effectively centered on the center of our coordinate system. So this is the leading behavior for small values of r of h1 and h2. In general, for hn, we have n-1 moments appearing. Actually, no, n moments appearing from L equals 0 up to L equals n-1. So in each order, you introduce a new set of multipole moments. So what this means is, as you go to higher order in perturbation theory, you effectively see more structure of the small object. So leading order, you just see the mass. The next order, you start to see spin and displacement of the mass away from the center of your coordinate system. Next order, you start to see quadrupole moments. Then you see octupole moments. The higher order you go, the more structure you see of the object. So for the purpose of these lectures, what I've said already is all that you need to get out of the matching condition. All you need to know is how the outer metric perturbations, Hn, are restricted in the powers of 1 over r, and how the multipole moments of the inner background metric fix the coefficients of those leading powers. You don't need to know anything else about the inner metric. All you need to know is what are the multipole moments defined from G object. That would change if you then go to third order, where the quadrupole moment appears. And the reason that would change is that we're going to be working outside of the object, just solving Einstein equations for H1 and H2 in vacuum. And the Einstein equations do not determine the evolution of the quadrupole moments. The Einstein equations do determine the evolution of the mass and of the motion of the object that's encoded in mi, and the evolution of the spin, but they do not determine the quadrupole moments. The quadrupole moments are only determined once you have some equation of state for whatever your small object is. So at that order, you would then need to do a more complete matching, where you actually solve the inner expansion up to sufficient order in order to find out what is the quadrupole moment corresponding to a particular equation of state, say if you have a neutron star. But for us, all we care about is we've got some multipole moments that appear in H1 and H2. That's all we need to know. Okay, so what we're going to do is take this general form and start solving the Einstein equations near the small object, but still outside the small object. And from that, we're going to get the self-force, and we're going to get more complete information about the form of the metric near the small object. And these are going to be the main outputs of this whole local analysis. And we need both of them for what comes afterwards. Okay, so let's adopt coordinates t, x, a. So local coordinates txa that are centered on some world line that lives in the manifold of the external background spacetime. So we're imagining, okay, we look at the manifold without the small object in it. We place a curve in that manifold, call it gamma. And we're going to have coordinates where t is the proper time along that curve. And the Cartesian coordinates xa point orthogonally away from the curve. So these coordinates are called Fermi-Walker coordinates. I'm not going to go into detail of how you actually construct them and how you find the background metric in these coordinates, but the key thing is that the background metric, external background metric, G alpha beta, just looks like Minkowski plus corrections of size r. So if this curve is accelerating, which it is for us, or we will find that it is, at order r, you have an acceleration term. At order r squared, you start to see the effect of the curvature of spacetime. So you start to see the Riemann tensor appearing. But we're not going to worry about those details. Okay, so here I've just said, okay, I've got a coordinate system in the manifold of the external background. How is this related to the position of the object? So I'm going to try to illustrate that with a picture. So how is gamma related to the position of the small object? Okay, let's say this is a picture of the space-time near the small object. You've got some fairly strong curvature very close to the object. So this could be a black hole, in which case the curvature would go down indefinitely. Or it could be a neutron star, in which case the curvature is finite. And now we're performing two different expansions of this around two different background metrics, and therefore potentially around two different manifolds. Particularly if this is a black hole, the manifold in the outer expansion will be different than the manifold in the inner expansion. So this is the small object here. So in the outer expansion, you're looking, let me get that over here. You're looking at just a nice, smooth manifold, and then you add perturbations, little h, on top of that nice, smooth manifold. Then, in the inner expansion, you're zooming in on the region near the small object. Make this a little bit closer to the object. Like that. So in here, we've put a curve gamma. Now, through this diagram, we're relating the position of that curve to the position of the object. So in particular, here, in the coordinates t, x, a, we measure the mass dipole moment, and we set it equal to 0. So these coordinates are only defined in some region in this manifold around this curve gamma. But then through these maps, that defines the coordinates, at least until you get very near the small object. You have those same coordinates defined here. So we can measure the mass dipole moment in those coordinates, and then when we set it to 0, that means we are effectively setting this curve here to be the center of mass of the small object. So if this is just a smooth body, all the manifolds are the same. You have different metrics, but they're all the same manifold. And then you can just put this curve smack down right in there. But if it's a black hole, well then no, this goes down forever. And you don't have some time-like curve inside the black hole. That's not the way black holes work. But nevertheless, we can identify a representative center of mass world line for that little black hole. And that lives up here, but it corresponds to the center of mass because down here, we're setting the mass dipole moment to 0 in these coordinates txa that are centered on this curve. All right? So that's how we decide or define what we mean by the world line of the little black hole. Okay, now what's our overall strategy? As I said, we're going to solve the Einstein equations. We're going to work in the self-consistent framework. Remember, the defining feature of the self-consistent framework was that we don't perform a Taylor series of this world line gamma. We treat it just as some accelerating curve that depends on the value of epsilon. We're then going to solve the first order Einstein equation, but we're going to be working in this buffer region out here. We're going to be working in the buffer region, which is outside of the object, so we're in vacuum. We don't have a stress energy tensor on the right-hand side. And the second order equation, so these are both, this E, remember, is the Lorentz gauge Einstein, linearized Einstein tensor. So this was just box of H alpha beta plus 2 times the background Riemann tensor. So we're solving these two wave equations for H1 and then for H2. So once we've solved these equations, we're not going to completely have determined H1 and H2, because these equations don't contain the full information of the Einstein equation. You're only containing the full information when you also impose the Lorentz gauge constraint. So we substitute the solution we get from this into the gauge condition. And the way this works is that these equations can be solved no matter what the mass is, no matter what the spin is. It doesn't matter if they're evolving with time. They can be completely arbitrary. And also, no matter where the center of mass is. You can have an arbitrary curve, and you can still get the solution to this equation. So all those things are going to be determined by the gauge condition. So this determines m dot, the rate of change of the small mass. It determines si dot, the rate of change of the spin. And it determines a alpha, which is the covariant acceleration of the curve gamma that is the center of mass. So all this comes out of imposing the gauge condition on top of the solution to the wave equation. Okay. To start, notice that a spatial derivative, d dxi, so lowercase Latin letters always correspond to a spatial coordinate. This lowers the power of r by 1 power when it acts on something. So for example, if we're acting on r to the p, we get p r to the p minus 1 times just the derivative of r. And this derivative of r is that unit vector ni, but just with index lowered using Kronecker delta. So I think I actually asked you to establish this as one of the exercises. So ni with index up is defined to be just a coordinate xi over the distance r. And that's a unit vector that points radially outward from the world line. So this derivative has brought the power of r from p down to p minus 1. But time derivatives do not lower the power of r. So if you're looking at small values of r near the world line or near the small object, spatial derivatives dominate over time derivatives. So this dominates over a time derivative. So effectively that means we have kind of a quasi-static scenario where the time scale is much longer than the spatial scale. So we can use that to considerably simplify the structure of the equations. So let's say we're looking at the box operator acting on h bar n. So this could be h bar 1, h bar 2. This is the background metric contracted into two derivatives of h bar n. And then we can think, okay, this background metric is approximately Minkowski plus order r terms. These derivatives, well, you have things that are like just two partial derivatives acting on h bar n. And then you have things that are Christoffel symbols. So these are Christoffel symbols of the background spacetime in our local coordinates, times partial derivatives. And then you have derivatives of the Christoffel symbols times h bar. And finally, you'll have things that are products of Christoffel symbols. So how do each of these terms scale with r? What is the dominant thing? Well, the dominant thing is when this is two spatial derivatives. So that's like 1 over r squared times h bar n. The Christoffel symbol is order r. Actually, no, it's order r to the 0 because you have an accelerating coordinate system, so it's not entirely inertial. So this is r to the 0. It doesn't vanish on the world line. The term that doesn't vanish is proportional to the acceleration of the curve. Then this is of order 1 over r to the h bar n if this is a spatial derivative. So this whole thing is 1 over r times h bar n. Here you don't have any derivatives. Here you don't have any derivatives of h bar. So these are both of order just h bar. The Christoffel symbols can't give you a negative power of r. So the dominant piece in this entire expression is just the term where you have two spatial derivatives. And that's getting contracted into Minkowski metric. So the spatial part of the Minkowski metric is just the ordinary Euclidean metric, delta ij. So this whole thing, at leading order, reduces to delta I of h bar n alpha beta plus order r minus h bar n. So this is just the flat space Laplacian. dx squared plus dy squared plus dz squared. What this is going to do for us is turn these equations we got over here, these two wave equations, when we expand in powers of r and solve order by order in r, what we're going to be solving is just a sequence of flat space Poisson equations, where you have flat space Laplacian of some quantity is equal to some other quantity, and you just solve as you would always solve the flat space Poisson equations. Okay, so I don't have time to go into the next bit. Actually, no, let me write one more thing. So you also have that Riemann term in these wave equations. So the Riemann tensor is again order r to the 0. So this is order r to the 0 times h bar. So that means that those equations over there, or that operator E alpha beta acting on h bar n, can be written as flat space Laplacian acting on h bar n plus a sum of higher order terms, higher order in powers of r. Which I'll write as E superscript P alpha beta of h bar n, where this operator E superscript P is always of order r to the p times h bar n. All right, then the idea is we're going to move this to the right-hand side of the wave equations and just keep solving for things that are being operated on by the flat space Laplacian. All right, so we'll end there and finish this tomorrow. Any questions? For white dwarfs, also necessary.
Because of the
less compact the object becomes, the less accurate the inner expansion is going to be. Because the less compact an object is, the more its higher multipole moments start to dominate. So here, in the scaling, where I've said, okay, everything on the inner expansion is a function of just r over epsilon, effectively, that assumes that there's only one scale for the small object, which is set by the mass. So it's assuming that the length is of order the mass. So if you have something where that's not true, and it's only really true for neutron stars and black holes, or maybe some more exotic objects, if that's not true, then your approximation is going to get worse and worse because you're not including enough information from the higher multipole moments. So you could tweak this to be a multi-parameter family of solutions, where you have length parameters that are not associated with the mass.
So for the case of, let's say, if I want to study tidal disruption of a big star, in that case, I don't have to do the matching condition, but still have to I cannot take points.
It's not that you don't have to do the matching condition, it's that this entire setup is not going to work very well.
Okay.
So you'd have to do something different to deal with that. Especially if the disruption is happening on a quick time scale. So this assumes that this setup assumes there's no fast time scale of the small object. You only have the orbital time scale is your fastest time scale, then you have the radiation reaction time scale much bigger than that. You don't have any really fast internal dynamics in the setup. So if something happens on the time scale of the small object, like if you have a neutron star that's pulsating quickly, this setup is not going to capture that at all.
Both time scales are here not related to the internal time scales.
Yeah, exactly. So that's why things look effectively quasi-static. If you had things operating on a really fast time scale of the internal dynamics, then this would not be suppressed relative to that. They would be of the same order.
Thank you.
No? All right, let's break for lunch then.